Hello class, this is for help on page 31, number 5, where we have this amusement park ride that's spinning in a circle. As it's spinning in a circle, you're on the ride and the floor begins to drop. It goes from this level A to level B. And as it goes from level A to level B, you stay up against the wall. And you're up against the wall even though there's no floor. And that's because there's this force due to friction that's holding you up. So I drew a free body diagram where you still have gravity pulling you down, but the wall is holding you up. This frictional force is holding you up. And the wall is also pushing against you towards the center of rotation. So I have this normal force that's going towards the center. So I tried to draw as the guys right here up against the right-hand side, so that way we can have the normal force going towards the center of the circle. And so this would be the free body diagram that we have here, where this frictional force is equal to the gravitational force down. You don't want to have one bigger than the other, otherwise you're going to be accelerating down, falling down, and that's not fun in an amusement park ride. You want the floor to go and you are suspended, so this force up equals this force down. So there's 3 equations over on this right-hand side that we are going to be using. This force due to friction is mu, that's the coefficient of friction, times the normal force. We also know that velocity is your displacement over time. So we can really use the speed, the instantaneous velocity, is going to be as they go around this circle, they have to go around it 2 pi r, that's the distance it travels, over the amount of time that we're being asked to solve. This problem is trying to get us to find that amount of time. How long does it take to go around one complete period of rotation, one complete time? So this period of rotation, that is the time that we're trying to find. Last equation that we're going to be using is this Fc, that's that centripetal force, is mv squared over r. So this is the force of something moving in uniform circular motion. So to start, we're going to start off by taking this force due to friction, that's up, and we're going to set it equal to this mg down. So this force due to friction, which is up, this equals mg down. Now we know the mass, and we know what g is, that's that 9.8, that's the acceleration due to gravity. And we know an equation for this frictional force, that's this mu times the normal force. So now we're just going to put that in for the force due to friction. Mu times the normal force is equal to mg. Now we need to recognize the normal force, that is the force acting towards the center of this circle. That normal force is that centripetal force. It's a fake force. It's not really anything real, it's just something that comes as a result. So the normal force, that's the wall pushing against us, that's what keeps us in the circle, but it's going to behave by this mv squared over r. So now we're going to get mu times a normal force, which we know is now mv squared over r, is going to equal to mg. So we can look at this equation, we can already see that m on one side and m on the other side cancels out. So we're going to have this m cancel out, which is a good thing. This should not be a mass-dependent ride to where a low mass and high mass amusement park rider would experience a different amusement park ride. So we can see that mass is not important here. So we're going to try to, once again, we are trying to solve for this t, this time. And we know that time is going to be embedded in this velocity equation. So I'm going to try to solve for this velocity. So I'm going to multiply by r on both sides. So I'm going to multiply it by r. And I'm going to divide by mu on both sides. So now on my left-hand side, the r's cancel out, the mu's cancel out, giving us v squared is going to equal to gr on mu. So v squared is going to equal to gr on mu. We know what mu is. We know what g is. We know what r is. The r is given as 1.5 meters. So now we can square root to get v is the square root of g r on mu. Now I'm going to plug in for what v is. We know that v is 2 pi r divided by the time. So if this is 2 pi r divided by the time, this is going to equal to the square root of gr on mu. I'm going to try to solve for the time. So I'm going to multiply by time on both sides. So now time is going to cancel out, and I'm going to divide by the square root of gr on mu on both sides. So now on the right-hand side, we have t. On the left-hand side, we have 2 pi r divided by gr on mu. So t, which is what we're trying to find, is going to equal to this 2 pi r divided by the square root of gr on mu. Now you could simplify this down and get to a more simplified way of typing into your calculator, but we know what 2 is, we know pi, we know r, we know g, we know r and mu. So once you type this into your calculator, I get a value of about 1.73 seconds. So that's the amount of time it takes to complete one period of rotation.